Section 8.3 talks about volumes of revolution using the cylindrical shells. Suppose I'm looking at y equal f of x, just like before, and I'd like to run this from A to B. Again, if I take this area, which is 2 dimensions, and if I rotate that about the y-axis, obviously it's going to create an identical copy like it, and it's going to occupy about right there. As this rotates, it's going to create a volume. Now, if I pick my rectangles parallel to the axis of rotation, if I call this x sub 0, call this x sub n, and if I pick my rectangles parallel to the axis of rotation, x sub 1, x sub 2, x sub 3, and the list goes on, x sub n minus 1. Now, as this rotates, when I pick this, I'll notice it's going to create an identical copy like it right there. And as this piece rotates, I see a cylinder, and that's where the name cylindrical shells come from. So I'm going to take and I added x sub 1. Oops, that didn't register. Here we go. And then from x sub 1, next one is the blue. So keep in mind the inside is hollow. We're talking about the surrounding of this. So the inside is empty. And if I go after that, and of course that's getting bigger and bigger. And if I get to the very last one, I know this is a hard color to see. And if I add these volumes, I could say the volume is roughly this. Well, if I take this and I cut it, if I cut this along, let's say right there, cut it and open it flat, it would look something like this. Kind of like, let's say you have a soda can and let's say it's open at the top and the bottom, and if you just cut the side and open it flat, it's going to look rectangular. Plus, then you're going to have another rectangle. And the list goes on. And the last piece is going to have well, the way it works, if I really think about it, this thickness is pretty much delta x. So this is delta x, this is delta x, this is delta x, right? This height here that is f of x sub 1. Here, it's f of x sub 2, and you can see it right there. And the reason we're putting approximately, because this is not a straight line, this is a curve. I'm drawing that as a straight line. So I'm going to say that's a rectangular prism, even though this top right here is curved. I'm assuming it's straight. That's why I'm saying this is an approximation. And the list goes on until I get to the last one, and the height is f of x sub I. Now we get to the tricky part. If I want to know what this length is, this length resembles the surrounding of a circle. That's 2 pi. And do you see that the radius is x sub 1? When I get to the next piece, this surrounding is the circumference of a circle. That's 2 pi, and the radius is x sub 2, and the list goes on, where this is 2 pi, and the height is f of x sub n. So I could say, wait a minute, I could say the volume is roughly length times width times height. So that is 2 pi x sub 1 f of x sub 1 delta x sub 1 if you want, but it doesn't matter because they're all the same. 2 pi, I'm talking about delta x, f of x sub 2 delta x plus, and the very last piece, 2 pi x sub n, f of x sub n delta x. And I could say this is the series I equal 1 to n of 2 pi x sub I f of x sub I delta x, and you know the drill. If I wanted those curved to be really straight, I have to create an infinite amount of those shells, meaning I want those to be infinitely close to each other. Then that curve will start looking more flat. So if I take the limit as n approaches infinity, I'll get the volume to equal the integral from a to b of 2 pi x, that's the radius, f of x, that's the height, and dx, that's the thickness. So basically, this is what I have to do every time to figure out the volume of the revolution using the cylindrical shells. And all what I have to do is pick my rectangles parallel to the axis of rotation. Well, let's play with that. Now there's a small thing you have to do on every problem, but for the most part, it turns out to be really simple. So, directions. For the following exercise, find the volume generated when the region between the two curves is rotated about the given axis. Use the shell and the washer method. So they want us to use both the shell and the washer method. Well, let's set up the first problem. Here it says y equal 3x 0, 0, when x is 1, y is 3. Oh, and y equal 3, and the y-axis. So they're talking only about this region. Now, practice. I'm going to set those up. So let's see how this is going to be. The region in question is right there. I'm going to rotate this about the y-axis. So they want us to use the shell method and the washer method. Let's do the washer because we are used to it. Washer slash disk. This is, oh, I should have did that for both. That's okay. This is going to create an identical copy like it right there. There it is. So if I pick my rectangle washer perpendicular to the axis of rotation, then this is going to create an identical copy right there. And I'm looking at this disk and the radius of the disk. So this is okay. What's going on? The radius of this disk is simply that distance. Now, volume is going to be the integral. This is with respect to y. Y equals 0 to y equals 3 because that's the point 1, 3. Since I'm picking it sideways, perpendicular to the axis of rotation, I'm looking simply for that area. That area is pi times the radius squared. And what is the radius? Well, this is y equal 3x. Remember, if this is dy, you're going to solve for x. And there it is. And if I work this out, that would be the integral of pi over 9y squared dy 0 to 3. That would be pi over 9 times y cubed over 3. So that is pi divided by 27 times 27 minus 0. That will be pi. Okay. Now, if I want to use the cylindrical shells, I'll pick my rectangle parallel to the axis of rotation. This piece will create an identical piece like it right there, and you could see the cylinder right in front of you. Volume is going to be the integral. Since I'm picking it vertical, that's a dx. X runs from 0 to 1. 2 pi, the radius, times the height. Well, here's the deal. Every time you start the problem, you run from the origin, always from the origin. If you picked your rectangles vertical, you call that x, and you proceed. But look at that cylinder. Isn't that cylinder looking like this? Isn't that x that you pick the radius? And isn't the height top minus bottom? Isn't the top 3 and the bottom is y equal 3x? So how does that work? That is 2 pi, the integral from 0 to 1 of 3x minus 3x squared dx. That's 2 pi times 3x squared over 2 minus x cubed. That is 2 pi. Plug the 1 in, 3/2 minus 1. And that will be 2 pi times 3/2 minus 1. That's 1/2. And the 2's cancel out. And there it is, as you see. You can't get it wrong. So we're going to focus on the shell method here. I'm going to set up both of those, of course, but Oh, 114. What's the difference? The same problem, the same graph, but we're going to rotate it about the x-axis. So if I'm going to rotate it about the x-axis, what's going to happen? Let me see. Is it still in there? Would be nice. Yep, it is. Very good. Okay. Here we're going to do slightly different. Oh no, that was fun. Okay. And let's look at that now. I'm going to rotate this about the x-axis. So the same exact region, nothing different. Well, if I rotate it about the x-axis, that's going to create an identical copy like it. Right there. Okay. If I want to use the washer, which is what I'm used to, I'm going to pick my rectangles perpendicular to the axis of rotation. That's going to create a copy like it right there. Let me color code those. This is y equal 3. Do you see that the outer rim of that is actually the purple? And the distance of this is pretty much 3 units. So if I say volume equal the integral of pi times 3 squared, that's going to find all of this. But you do know that this has a hollow part inside. The hollow part inside is based on the green. Well, the green, the radius of that is pretty much the distance to the green. Remember that was y equal 3x since it's vertical. So if I subtract off this piece, with respect to x runs from 0 to 1, that will find me that volume. That would be the integral from 0 to 1. Pi I'll factor out. That's 9 minus 9x squared dx. That would be pi times 9x minus 9x cubed divided by 3. That makes it a 3. That is pi times 9 times 1 minus, this is 3 by the way, 3. That will be 6 pi. And if I decided to use the new technique, I'll pick my rectangles parallel to the axis of rotation. The cylinder is right there, it's sideways. Volume is going to be the integral. Since I'm picking this sideways, that's a dy. Y runs from 0 to 3. And I'm going to go from the origin and run to my rectangle. If it's on the x-axis, I call it x. If it's on the y-axis, I call it y. And you notice that that turns out to be the radius of that cylinder. And the height is right minus left. This is y equal 3x. Remember, if this is dy, x equal y over 3. Setup, that will be the setup. And if I say setup, that will be the setup. Now, if I work this out, again, I'm going to work this as well. And after that, I'll just set them up. The 2 pi over 3 is a constant. Y squared dy, yeah? So that would be 2 pi over 3 times y cubed over 3 evaluated from 0 to 3. That will be 2 pi over 9. If you plug that in, that's 27 minus 0. 9 divides 27 3 times, and that's 6 pi. So you can't get it wrong. How do you find the volume? Irrelevant. You want to use the washer, but you gotta follow directions. So I want to set this up as well. Y equal 2x cubed. If I take y equal 2x cubed, now I have to rescale this a bit. From x equals 0, so x equals 0 is that line. X equal 2 is that line. 0, 0. If I put 2 in, I'll get 16. So I'm going to say this is 4, 8, 12, and 16. Of course, it should look more like this. And there's a continuation to it, but we're only interested in quadrant 1 in this case. Most of the time that's the case. That's the region that they're talking about. Now we're going to rotate this about the y-axis. If we rotate it about the y-axis, we're going to create an identical copy like it right there. And it's going to occupy that much as well. Now, let me copy that so we can set them up for both directions. Hopefully that's going to pick it up. That's pretty good. So here I'm just going to set them up. Okay. Now, if I pick my rectangle washer method, so disk slash washer, I pick my rectangle perpendicular to the y-axis. Do we see that the outer rim is the green function? And the green, that distance is simply 2 units. So volume equals, since I went sideways, that's dy. And it's going to run from y equals 0 to y equal 16. And it's going to be pi times x equal 2 squared minus pi times and do we see that the hollow part is right there? And that radius right there is right minus left, but this is y equal 2x cubed. If I'm going with dy, I need to solve that for x. That will find me the volume. This is the setup. I'm going to assume we can work those out. Now, what if I decided I want to use the cylindrical shells? I'll pick my rectangle parallel to the axis of rotation. This will create a copy like it right there, and the cylinder is right there. Volume is going to be the integral. This is vertical, that's the x. X runs from 0 to 2, and I'm going to go with 2 pi, the radius and the height. Well, I know the drill. I'm going to run from the origin and call that x. In this case, I notice that that's the radius. Now, that's not always that's the case 85% of the time. As long as you're rotating about the x-axis or y-axis, that's true. But pretty soon we're going to rotate about something else. The height happens to be the top minus bottom. This is y equal to x cubed, so top minus bottom is 2x. And there it is. The setup for the shell method, most students say that's easier. To me, they're the same, but you know, whatever works. Have it here. Use the shell method to find the volume of the solid. Note that the rotation lies between the curves and the x-axis, and you rotate about the y. Okay, so they're always going to go between the curves and the x-axis, and the rotation in this case is about the y. Well, y equal 1 minus x squared. If I say that is 1, that is 1, that is 1. So 1 minus x squared, I want it between the x-axis. It says x equals 0. They're going to chop off. They're talking about only that portion of the parabola. I know the parabola runs this way. But they only want in quadrant 1, it seems. Oh boy. That's not what I meant. That's what I meant. Sorry. Okay. And if I rotate this about the y-axis, what's going to happen? it's going to create an identical copy right there. It's going to occupy that piece right there. Now, let me label. This is y equal 1 minus x squared. And to find the volume using the cylindrical shells, that's 2 pi times the radius, the height, and I'm going to pick my rectangles parallel to the axis of rotation. That tells me it's a dx because it's vertical. There's my cylinder. I'm going to go from the origin to wherever the rectangle that I picked called that x, and you notice in this case that happened to be the radius. The height is top minus bottom. Since that's a dx, the top is 1 minus x squared minus 0, and x runs from 0 to 1, and there it is. The next problem, y equal 1 over x, x equal 1. So x equal 1 gives you a 1. X equal 100 gives you 1 over, let's say this is 100. So we're talking about this. Of course, the graph looks like this, but we're chopping that off from 1 to 100. We're talking about that piece, which is this piece right here. I'm going to rotate this about according to what they said, the y-axis. That's going to create an identical copy like it right there. And it's going to look something like this. When I take the volume, 2 pi, the radius, notice I don't fill anything until I pick my rectangles. I'm going to pick my rectangle parallel to the axis of rotation. Well, if I pick it vertical, that's the x automatically. Then I know x runs between 1 and 100. And if it's the y, I have to solve for y. And the cylinder is right there. It's a very thin cylinder, but it's right there. I go from the origin to wherever I picked that rectangle, called that an x, and I notice that that is the radius. And the height is top minus bottom. Top is 1 over x, bottom is 0, and there it is. All right. What if I rotate about the x-axis? Okay. What is that? So let's make sure we get the region right. This says take y equal 1 minus x squared. That's half a circle. Let's say that's 1, that's 1, that's 1. Y equal, that's the upper half of a circle. So for the following, use the shell method to find the volume generated by the region between y equals 0. This is y equals 0. The x-axis, again, they just want that piece. And the equation for that is y equal 1 minus x squared under a radical. Okay, I'm going to rotate this about the x-axis. So that's going to create an identical copy like it right there. It's going to occupy all of that. So volume is going to be the integral 2 pi, the radius, the height, and I'm going to pick my rectangle parallel to the axis of rotation. That makes it a dy. So y runs from 0 to 1. There is my cylinder. I'm going to run from the origin to my rectangle. If it's on the y-axis, I call that a y. That turns out to be my radius most of the time. And the height is right minus left. Now, do you notice this is a dy? I can't put the square root of 1 minus x. You can't have an x and a y. So I need to solve that for y. I'm going to square both sides. Swap those. So here, square both sides. Swap those. And if I take the square root, I'll pick a plus or minus, but in quadrant 1, they're all positive. That turns out to be an identical because it's a circle. And in a circle, everything's symmetric. But that's not normally the case if this was an ellipse or a hyperbola or anything like that. Okay, the following problem again. Y equal x cubed divided by 2. So x equals 0. If we put 2 in, that will be 4. So a cubic looks like this. It's kind of like a parabola but steeper. X equals 0, X equal 2, and they did say x-axis. They're talking about this. We're going to rotate this down about the x-axis. Here we are. If you pick your rectangles parallel to the axis of rotation, the radius, the height, and I picked it sideways, that's dy. Well, we know this is y equal x cubed over 2. We know that's x equal 2. dy, y runs from, if we put 2 in there, 2 cubed is 8 divided by 2, that's 4. So we run from 0 to 4 because that's a dy. We run from the origin, we call that y, and you notice as this rotates, that happened to be the radius. Now the height is right minus left. Right will be x equal 2 minus left, 2y equal x cubed, x equal cube root of 2y. There it is. And of course you integrate that. I'm going to assume you could do those. So I'm setting those up just so that I can do as many as possible. And the following problem, how about x equal radical y plus 1? Okay, well, y equal, all you could say x minus 1 equal radical y, y equal x minus 1 squared. So that's shifted 1 unit to the right, and it opens up. So when we say x equal square root of y plus 1, we're talking about when y equals 0, x equal 1. When y equal 1, x equal 2. We're talking about this piece of the graph. We're going to chop it off. We're going to start x equal 1. Okay, right there, x equal 3. Right there, the x-axis. And I think, yeah, we're going to rotate around the x-axis, all of those. So if I rotate this about the x-axis, after a while they all look alike. Doesn't matter what the shape look like. It's the same work. Volume equal the integral of 2 pi, the radius, the height, and I'm going to pick my rectangle parallel to the axis of rotation. That makes it a dy. Y runs from 0. If I put a 3 in for x, to 4. I'm going to go from the origin, call that a y, but you notice that that's the radius of the cylinder. And the height will be right minus left. This is x equal 3 to x equal, make sure you use parentheses, square root of y plus 1. And that will find me the volume using the cylindrical shells. Couple more problems to go, almost done. I want to take y equal, oh, that's the last one. This is the difference. Before, this used to be a big deal. Now they're kind of cutting down on that, which is fine, whatever works. So I'm looking at y equal radical x. Let's color code those. 0, 0, 1, 1. So it looks like that. I'm going to take y equal x squared. So I'm going to enlarge that a bit. I'm going to go ahead and make that a bit long. So I'm going to say that's a 1, that's a 1. The radical looks like this. And the square look like this. They're talking about this region. I'm going to rotate this above the line x equal 2. Well, it's going to create an identical copy like it right there. Oops. There we go. There we are. And if I pick my rectangles parallel to the axis of rotation, there it is. The cylinder is right there. The volume is going to be the integral. Now, since I picked it vertical, that's at the x, so 2 pi, the radius, the height, and x runs from 0 to 1. That's simple. Now, I'm going to run from the origin, and I'm going to call that an x. But do you see that's not the radius? The radius is actually right there. Isn't that the radius of this? If this is x, right, and this is 2, isn't the radius right minus left? And the height, if I run the height up, if I look up, isn't the height top minus bottom? The top is the purple, and the base is the green, and that will find me the volume of what I want. And that's pretty much it for this section.